Hello friends, in today's episode we are going to discuss coordination compounds. Coordination compound is an important chapter in 12th class chemistry. So first we start with introduction to coordination chemistry or coordination compounds. Transition metal possess characteristic property of undergoing complex formation. Due to this remarkable tendency, they form a large number of coordination compounds. The tendency to form coordination compound of several non-transition metal atoms have much less than transition metals. Coordination compounds are the compounds in which the central metal atom is linked to a number of ions or neutral molecules by coordination bond or coordinate bond. Coordinate bond is a covalent type bond in which both the shared pair of electrons are contributed by one atom. Coordinate compounds are widely distributed in minerals, plants, and animals and are known to play many important biological functions. Coordination compounds examples. For example, chlorophyll is a coordination compound of magnesium and it is essential in photosynthesis. Red pigment hemoglobin is a coordination compound of iron. The branch of chemistry which deals with the study of coordination compounds or complex compounds is known as coordination chemistry. Werner's theory of coordination compound. Basic postulates of Werner's theory. First, most of metallic elements exhibits two types of valency, primary valency or principal valency and secondary valency. Second, every metal tends to satisfy both of its primary and secondary valencies. Third, every metal has a fixed number of secondary valencies. Fourth, the secondary valency is always directed towards fixed position in space. Werner's theory in the light of modern electronic theory of valency. According to Werner's, two spheres of attraction are present around the metal. The inner zone is coordination sphere and the outer zone is ionization sphere. In terms of modern electronic theory of valency, the coordination sphere is equivalent to the coordination number of the metal ion and the ionization sphere is equivalent to ionizable or the oxidation state of the metal ion. Werner introduced a square bracket to enclose the central metal ion and the ligands. This represents coordination sphere. The ion of ionization sphere are placed outside the square bracket. For example, CO in brackets NH3 then 6 bracket close Cl3. In this complex, the coordination sphere includes 6 ammonia molecules while ionization sphere includes 3 chloride ions. Application of Werner's theory to CO3 amine in coordination compound class 12. CO3 amines are the complex of CO3 with ammonia. They have compositions like CONH3 5Cl2, CONH3 5Cl2, CONH3 4Cl2 Cl, CONH3 3 Cl3. Dear friends, to see examples with brackets clearly, visit our website www.chemistrynotesinfo.com or www.chemistrynotesinfo.blogspot.com. Experimental observation to CO3 amines. The primary valency or oxidation states of cobalt is 3 while secondary valency or coordination number is 6. When cobalt amine are heated with hydrochloric acid at 373 Kelvin, ammonia is not removed or evolved. In all these compounds, ammonia molecule are seen to be firmly bound. All these compounds are found to differ in their electrical properties. All these compounds are differing in their reactivity towards silver nitrate. Ligands. The molecules or ion which are coordinated to the central atom or ion in the coordination compound are called ligands. Example, in NH3 6 2+, central metal ion is Ni2+, and ligands are NH3 molecules. In CrH2O6 3+, the central metal ion is Cr3+, and ligands are H2O molecules. Types of ligands. Types of ligands and classification of ligands is as follows: mono or unidentate ligands. The ligand molecule or ion which has only one donor atom and one point attachment and can coordinate with the metal ion at only one site in a complex is called unidentate or monodentate ligands. Example, Cl-, OH-, NH3, H2O, etc. Multi-dentate ligands. The ligands molecule or ion in which has two or more donor atoms or points of attachment and can be linked to the same metal in a complex using two or more donating sites is called poly or multi-dentate ligands. Depending upon the number of donor atoms, they are further classified as bidentate ligand. Example, ethylene diamine. Tridentate ligand. Example, diethylene triamine. Tetradentate ligand. Example, triethylene tetraamine. Hexadentate ligands. Ethylene diamine tetraacetate, EDTA. Ambidentate ligands. Ambidentate ligands are the ligands which have two or more donor atoms capable of forming coordination bond. However, only one donor atom is utilized during complex formation. Example, NO2 group has donor atom N and O, but out of the two, only one donor atom is linked to the two. Only one donor atom is linked to the metal as MONO or MNO2. Coordination number. The number of ligands which are directly bonded to the central metal atom or ion in a complex is known as coordination metal of the metal atom or ion, is abbreviated as coordination number or CN. In case of metal chelates complex with polydentate ligands or ring structures, CN is the number of pair electron involved in the formation of the bonds between metal and ligands. CN is characteristic property of metal. Geometry and shape of coordination compounds is governed by CN. Metal ion and coordination number. Metal ion Ag+, oxidation state +1, coordination number 2. Example, AgNH3 2+. Metal ion Cu2+, Ni2+, Zn2+, Cd2+, Hg2+, Pt2+. In all of these, coordination oxidation state is +2 and coordination number is 4. Example, CuNH3 4 2+. Metal ion Fe3+, CO3+, Cr3+, oxidation state +3. Coordination number 6. Example, CONH3 6 3+. SN4+, PT4+, oxidation state +4. Coordination number 6. Example, PTNH3 6 4+. MO4+, oxidation state +4. Coordination number 8. Example MoCN8 4-. The coordination number of the metal ion is influenced by charge on the metal ion, charge on the ligand, the relative sizes of metal ion and ligands, the forces of repulsion between the ligands, etc. Complex ion. A complex ion is more or less stable charged aggregate formed when an ion, mostly of a metal, is directly linked to a group of neutral molecules or ion. Coordination entity. A coordination entity constitutes central metal atom or ion bonded to fixed number of ions or molecules. Coordination pair. The central metal atom or ion and the coordination group ligands attached to it are written inside the square bracket and is together called as coordination pair. Homoleptic and heteroleptic complex. Complexes in which a metal is attached to one kind of donor group are called as homoleptic. Complex in which a metal is bound to more than one kind of donor groups are called heteroleptic. Cationic, anionic and neutral complexes. Cationic complexes. A complex in which the complex ion carries a net positive charge is called cationic complex. Example CONH3 6Cl3. Anionic complex. The complex in which the complex ion carries a net negative charge are called anionic complex. Example K2HgL4. Neutral complex. A complex carrying no net charge is called a neutral complex. NiCO4. Charge number of complex ions. The net charge carried by complex ion is called charge number. It is algebraic sum of the charges carried by the central metal ion and ligands attached to it. Charge number of FeCN6 4- is equal to charge on Fe2 plus 6 into charge on Cn- ion, that is equal to plus 2 plus 6 into -1 is equal to -4. Coordination polyhedron. The spital arrangement of the ligand atoms which are directly attached to the central atom ion is called coordination polyhedron. The common coordination polyhedral are tetrahedral, square planar and octahedral. Double salt and coordination compounds. Double salt. Double salts are molecule or addition compounds which exist in the solid state but dissociate into their constituents ion when dissolved in water. Coordination compound. Coordination compounds are molecule or addition compounds which retain their identity in aqueous solution and shows properties entirely different from those of their constituent ions. Characteristics of complex ions. Generally, a transition metal ion is the central metal ion in a complex. An ion loses its individual properties and acquires the properties of the complex ion which it forms. The complex ion can dissociate to a slight extent in a solution, however, it retains its identity. The algebraic sum of the charge of constituent ion is the net charge of the complex ion. The stability of chelate complex is higher than those complexes which are similar but non-chelated. Effective atomic number EAN. Effective atomic number is the total number of electrons around the central metal ion present in a complex. It is the sum of the electrons of metal ions and the electrons donated by the ligands. EAN is equal to Z x plus y, where Z is equal to atomic number of metal, x is equal to number of electrons lost during oxidation of metal to metal ion, y is equal to number of electrons donated by the ligands. So I repeat, EAN is equal to Z minus x plus y. In ferrocyanide ion FeCN6 4 minus, Z is equal to atomic number of Fe is equal to 26. X is equal to number of electrons lost due to oxidation of Fe2 plus is equal to 2. Y is equal to number of electrons donated by 6 Cn minus, that is equal to 6 into 2 is equal to 12. Then EAN is equal to 26 minus 2 plus 12, that is equal to 36. So EAN of FeCN6 4 minus is 36. EAN of few metal ions, metal Ni complex NiCO, Z is equal to 28, X is equal to 0, Y is equal to 8, EAN is equal to 36. Metal Fe complex FeCN6 4 minus, Z is equal to 26, X is equal to 2, Y is equal to 12, EAN is equal to 36. Metal CO complex CONH3 6 3 plus, Z is equal to 27, X is equal to 3, Y is equal to 12, EAN is equal to 36. Metal Zn complex ZnNH3 4 2 plus, Z is equal to 30, X is equal to 2, Y is equal to 8, EAN is equal to 36. Metal Pt complex PtNH3 6 4 plus, Z is equal to 78, X is equal to 4, Y is equal to 12, EAN is equal to 86. Isomerism in coordination compounds. Isomerism is the phenomenon in coordination compounds having same molecular formula but different arrangement of the ligands around the central metal atom or ion in the space. Stereoisomerism. Stereoisomerism are those isomers which have the same composition of atoms or groups but they differ in the spatial arrangement around the central atom. Types of stereoisomerism: geometrical isomerism, optical isomerism. Geometrical isomerism. Geometrical isomerism is due to difference in the spatial arrangement of atoms or groups of atoms around the central metal atom or ion. This occurs in heteroleptic complexes. When two similar groups, ligands, occupy adjacent position, the isomer is called cis, and when two similar groups are arranged opposite to one another, the isomer is called trans. Dear friends, you can see its picture, means picture of cis and trans isomers on our website www.chemistrynotesinfo.blogspot.com, or alternatively you can also visit our Instagram handle @Jitendra Sandhu. Sorry, it's my personal Insta ID. You can visit our Instagram handle @chemistrynotesinfo to see these cis and trans pictures also, or visit our website www.chemistrynotesinfo.com. Another, it is present in square planar complexes with coordination number 4 and octahedral complex with coordination number 6. Square planar complexes Ma2 B2 N plus minus, Ma2 BC N plus minus, MABCD N plus minus, MAB2 N plus minus. Octahedral complexes Ma4 B2 N plus minus, Ma3 B3 N plus minus, MAA2 A2 N plus minus. Tetrahedral complexes with coordination number 4 do not show this isomerism as all the 4 positions are equivalent. Optical isomerism. Optical isomerism in coordination compounds arise out of chirality of the coordination entity. Chiral compounds do not have any element of symmetry and are optically active. Optical isomerism are non-superimposable mirror images of each other and are called enantiomers. Optical isomers rotate the plane of plane polarized light. The isomers which rotates the plane of plane polarized light in the clockwise direction is known as deform. The isomer which rotate the plane of plane polarized light in the anti-clockwise direction is called as L-form. Optical isomerism is not so common in tetrahedral and square planar complexes. However, octahedral complexes, bidentate ligands show optical isomerism. Some example of such type of octahedral complexes are as follows: MAA3 N plus minus, MAA2 A2 N plus minus, MAA2 AB N plus minus. Structural isomerism. There are 4 types of structural isomerism. First, ionization isomerism. Second, linkage isomerism. Third, coordination isomerism. Fourth, hydrate isomerism. So, we understand one by one. First, ionization isomerism. The compound which have same molecular formula but give different ion in solution are called ionization isomers, and the phenomenon is called ionization isomerism. Example: CONH3 SO4Br red violet, CONH3 Br SO4 red. Linkage isomerism. The compounds which have the same formula but differ in the linkage of a ligand to the metal atom or ion are called linkage isomerism, and this phenomena linkage isomers, and this phenomena is called linkage isomerism. Example: CONH3 NO2 Cl2 yellow, CONH3 ONO Cl2 red. Coordination isomerism. The compounds which have same molecular formula but different complex ions involving interchange of ligands between cationic and anionic entities of different metal ions are called coordination isomers, and the phenomenon is called coordination isomerism. Example: CONH36 CrCN6 and CrNH36 COCN6. Fourth, hydrate isomerism. The compounds which have the same composition but differ in the number of water molecules present as ligands and are as free water molecules in the crystal lattice are called hydrate isomers, and this formula is called hydrate isomerism. CrH2O 6Cl3 violet, CrH2O5 Cl Cl2.H2O blue green, CrH2O4 Cl2 Cl.2H2O green. Valence bond theory. It's a very important theory and many questions come in exams from this theory. So let's learn valence bond theory VBT. This theory accounts for coordinate bond formation due to the overlap of vacant hybrid orbitals of the central metal atom ion with the filled orbitals of the ligands, each containing lone pair of electrons. Silent features of valence bond theory. A central metal ion present in a complex provides a definite number of vacant orbitals s, p, and d for the formation of coordination bonds with the ligands. The number of vacant orbitals provided by the central ion is the same as its coordination number. These vacant orbitals undergo hybridization to form same number of hybrid orbitals. Each ligand has at least one orbital containing a lone pair of electrons. The geometrical shape of the complex ion depends upon the hybridization of the metal orbitals. The vacant hybrid orbital of the metal ion overlaps the filled orbitals of the ligands to form coordination bond between metal and the ligand. The coordination bond is stronger if the overlapping between the orbital is greater. If central metal atom contains, then it exhibits paramagnetic property. If central metal atoms contains no unpaired electrons, then it exhibits dimagnetic properties. Structure of complex compounds based on valence bond theory. NiCO4, NiCl4 2 minus, NiCN4 2 minus, CONH3 3 plus, COF6 3 minus. Limitation of valence bond theory. Valence bond theory cannot explain the spectral properties, colors of complex compounds. It cannot explain why some complexes are inner complexes for the some are outer complexes for the same metal ion in the same oxidation state. It does not provide quantitative interpretation of thermodynamic and kinetic stabilities of coordination compounds. There is no distinction between weak field and strong field ligands. It cannot predict if a 4 coordination complex will have tetrahedral or square planar geometry. It does not explain the order of reactivity of inner complexes of D3, D4, D5, D6 ions. It does not explain magnetic movements. Crystal field theory (CFT). This theory assumes that the interaction between the metal ion and ligands is purely electrostatic. When ligands approach central metal atom or ion, the 5 degenerate d orbitals of the central metal atom split up into level of different energy under influence of electrostatic field of ligands. Silent feature of crystal field theory. In a complex, the central metal atom or ion is surrounded by various atoms or group of atoms called ligands. The ligands are either negatively charged ion F minus, Cl minus, Cn minus, etc., or neutral molecules possessing lone pair of electrons like H2O, NH3, etc. In the neutral ligands, the most electronegative atom points towards central metal ion. Ligands and metal ion act as a point charges. Electrostatic interaction is present between electrons of metal and ligands. When the ligand approaches the metal atom, the electrons of the central atom and those of ligands repel each other. These repulsive forces destroy the degeneracy of d orbitals and split them into two groups called T2G and EG group. Electrons first occupy lower energy T2G level,
electrons occupancy is in accordance with Hund's rule. Crystal field theory does not account for covalent characteristics as orbital overlap is not considered. Crystal field stabilization energy CFSE determines the stability of complex nature, number of ligands and geometry of the complex determines the magnitude of CFSE, that is crystal field stabilization energy. Weak field ligands and strong field ligands. The ligands with small value of crystal field stability energy are called weak field ligands. The ligands with large value of crystal field stability energy CFST are called strong field ligands. Spectrochemical series. The arrangement of ligands in order of their increasing field strengths, that is increasing crystal field splitting energy values, is called spectrochemical series. Spectroscopy is used to determine the value of pairing energy P and delta 0. Spectrochemical series is shown below. I minus is smaller than Br minus is smaller than SCN minus is smaller than Cl minus is smaller than S2 minus is smaller than F minus then OH minus then C2O 2 minus H2O NCS minus EDTA NH3 EN CN minus CO. Limitation of crystal field theory CFT. It explains only about the central metal ion with d orbitals but does not explain about orbitals like s and p. The theory does not explain about bonding in pi bonding in complexes. In the spectrochemical series, water is a strong ligand than OH minus, which is not explained satisfactorily. According to this theory, metal ligands bonds is ionic but cannot explain partially covalent nature of the metal ligand bonds. Colors in coordination compounds. The crystal field theory explains the origin of color of coordination compounds. Color is due to DD transition. When complex compounds absorb light of particular wavelength, an electron is excited from lower T2G level to higher EG level. Due to this, the coordination compound has a complementary color. An octahedral complex TiH2O6 3+ with D1 configuration with one electron in lower T2G level. Complex absorbs light in the blue-green region. The electron is excited from lower T2G level to higher EG level. So reaction occurs like this: T2G1 E0G, when light absorbed H nu, then it goes to T2G G E1G. The color observed is purple color. CuH2O6 plus 2 absorbs red light and the observed color is blue. This is due to transition of one unpaired electron of D9 configuration. Relationship between complex entity and wavelength. Coordination entity TiH2O6 3+. Wavelength of light absorbed 498. Color of light absorbed blue-green. Color of coordination entity purple. Coordination entity COCN6 3-. Wavelength of light absorbed 310. Color of light absorbed ultraviolet. Color of coordination entity pale yellow. Coordination entity COCl NH3 5 2+. Wavelength of light absorbed 535. color of light absorbed yellow, color of coordination entity violet. Dear friend, visit our website and see many other examples. Bonding in metal carbonyl. Metal carbonyls are the organometallic compounds in which carbon monoxide CO act as the ligands. There is donation of lone pair of electrons of carbon of CO into the suitable empty orbitals of the metal atom. This is a dative overlap and forms a sigma MC bond. There is pi overlapping involve donation of electrons from filled metal d orbitals into vacant antibonding pi star molecule orbitals of CO. This result into the formation of MC pi bond. Stability of coordination compounds. The stability of coordination compounds depends on the metal ion and ligands. For thermodynamically stable compounds, this interaction is strong. The thermodynamic stability is quantitatively expressed in terms of stability constant, which is an equilibrium constant for the equilibrium between metal ion and the ligands. M A plus N L X minus arrow M L N B plus, where M A plus L X minus and M L N B plus are the metal ion, the ligand and complex respectively, and A plus X minus B plus are charges. The equilibrium constant for stability constant is expressed as K is equal to M ln B plus divided by M A plus L X minus N. High value of stability constants indicates greater thermodynamic stability. Application of coordination compounds. There are many applications of coordination compounds in different areas. Coordination compounds are used in extraction of metals, analytical chemistry, medicine, electroplating, estimation of hardness of water, modifying the redox behavior of the metal ions, biological systems. Dear friends, you can join us or join our social media pages at Facebook, Twitter, Pinterest, Instagram, Telegram. To search us, type chemistry notes info on these social platforms. Dear friends, these notes or these podcasts are free forever. It's our guarantee. You get these podcasts, these notes free from our websites, from our social handles, from our Telegram channel. And we do not ask for any fees or concession from you to learn chemistry. And if you want to help us or to grow the chemistry education, you can donate us on, and these donations are also we accept from our website route only, and we do not approach individually to anyone for donations. So if someone asks you to donate money on the behalf of chemistry notes info, then it's really a fake person. We do not ask individually. If you want to donate something, please visit our website www.chemistrynotesinfo.com and donate. And we also want to say that having a domain name like www.chemistrynotesinfo.com have some liabilities, and we have to pay some charges for it. So in future, if you see that website not opening with the domain name www.chemistrynotesinfo.com, then you may think that we do not renew it due to some financial issues. But alternatively, you can get the notes of chemistry from our Telegram channel, chemistry notes info, or you can visit our blogger page, that is chemistrynotesinfo.blogspot.com, because blogspot.coms are free domains by Google and it's remains free for forever, as Google says. So you can get these notes free of cost from blogspot website, that is www.chemistrynotesinfo.blogspot.com. So friends, see you soon, very fast in our upcoming podcast with new chemistry education. Thank you. Have a great day.